Hello, this is Jude Socrates, and welcome to a portrait of linear algebra. Today's video is about bijective operators and the inverse of an invertible matrix. So in our last video, we talked about injective and surjective linear transformations. So we're going to combine those two properties, and we will generalize it actually to any function on two sets. So we will combine the properties of injectivity and surjectivity to create what are called bijective functions. And we will, of course, focus on bijective operators when it comes to linear algebra. We will construct the inverse function of a bijective function or transformation, and we will define what an invertible matrix is. We will decide if a 2 by 2 matrix A is invertible or not, and if it is, then we are going to actually compute its matrix inverse. So that will come later in the video. And for the first part, for several minutes, we're going to talk about a general mathematical concept, the concept of bijectivity. So just be patient, okay? Computations are going to arrive later on in the video. But to prepare ourselves for what we're going to do later, let's review a little bit of trigonometry. We've all seen the cosine function and its twin, the arc cosine function, sometimes pronounced as the inverse cosine function. So in order to create this inverse cosine function, we need an original function to be one-to-one. And we know the horizontal line test. Now, unfortunately, the cosine function is not one-to-one. First of all, it's periodic. So every 2 pi, your cosine is going to repeat itself. But looking at this graph, if you look to the left, to the negative x direction, you already fail the horizontal line test. So what do we have to do? We're going to have to ignore all the negative values of x, and now we can focus on the positive values for x. And as we can see, cosine starts at 1, cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is negative 1, and now it starts to go back up again. So once you cross pi, once again, you fail the horizontal line test. But if we restrict the domain of the cosine function, therefore, to 0 to pi, then our function will be one-to-one on that restricted domain. And if we look, the range of the cosine function on that restricted domain will, of course, be from -1 to +1. So, in trigonometry, we said, if this is your function on the restricted domain, simply exchange the x and y coordinates, and you will get the inverse function. So here, cosine of 0 is 1, so therefore, inverse cosine of 1 is 0. So that is this point over here. Cosine of pi over 2 is 0, so therefore, inverse cosine of 0 is pi over 2. So that is that point over there. And last point, cosine of pi is -1. So therefore, inverse cosine of -1 is pi. Just to remind ourselves though, how do you compute an inverse cosine value in general? Okay, well, because the restricted domain for our cosine is from 0 to pi, we're basically looking at the upper half of the unit circle, where the angle is between 0, pi over 2, and pi. So we can ask, for example, what is the arc cosine of 1/2? So we need to ask, well, what is the angle between 0 and pi whose cosine is 1/2? Well, if you remember your trigonometry, that should be the angle pi over 3, okay? Because if we ask, well, let's check what is the cosine of pi over 3, and we get, boom, 1/2. What about negative 1/2? What is the arc cosine of negative 1/2? Well, it should be on the left side of your circle, and by symmetry, that angle should be 2 pi over 3. So let's generalize the concepts that we saw for the cosine and the arc cosine functions. Let's suppose that A and B are any two sets, and f is a function from A to B. So what that means is that for every input A from the domain capital A, there's a unique element B from capital B, such that B is f of A. So again, A is the domain of our function, and B is the codomain of our function, just as we defined them for linear transformations. We will say that f is injective or one-to-one if the only solution to the equation f of a1 equals f of a2 is a1 equal to a2. So if you remember, when we first defined one-to-one transformations, we did the negative, okay, or more precisely, the contrapositive, which was if a1 is different from a2, then f of a1 has to be different from f of a2. But it's more natural if we go to this form for the definition. Again, an implication and its contrapositive are logically equivalent, so we can use either one of them. We will say that the function f is surjective or onto if the range of f is the entire codomain B. What is the definition of the range of f? It is all the elements B in the codomain capital B, so that B is f of A for at least one A from the domain capital A. We will put those two concepts together now. We say that f is bijective if f is both injective and surjective. So our cosine function was one-to-one on 0 to pi. It passed the horizontal line test. And the range was from -1 to +1. The range is as big as possible. If we stopped at pi, then we will only get 0 to 1. It could be bigger. So by going all the way to pi, we get the range to be as big as possible from -1 to +1. So what I want to do here has absolutely nothing to do with mathematics, or does it? So suppose we have two sets. Our domain will be capital A, which will consist of the letters H, K, and M. And our codomain will be capital B, which will consist of the letters R, S, and W. What do those letters mean? Well, A will represent makes of cars, okay? So H will stand for Honda, K for Kia, M for Mazda. The codomain B will represent colors. So R will be red, my favorite color, S silver, and W white. My very first car was a red Honda Civic. It was so much fun. So we are going to construct a function from A to B, and we want it to be both one-to-one and onto. Okay, so one-to-one means that two distinct inputs have to produce distinct outputs. So what that means is that once we have an output for H, we cannot use that anymore for K and M. Okay, so why not? I like the letter red. I had a red Honda. So let's make f of Honda to be red. So f of H equals R. Okay, now what about the Kia, right? Well, we could have a silver Kia, or we could have a white Kia. It doesn't matter which one as long as it's not red. So let's say that the Kia is white. Okay, so f of K is W. So that means that M, the Mazda, cannot be red or white. So it has to be silver if you want a one-to-one function. Okay, now notice that something else happened. Because we only have 3 possible values, letters, for the codomain, notice that each and every one of them also appears. So not only is this function one-to-one, but as a bonus, it is also on 2. Could we do that if we had another color in capital B? What if we had blue, little b? Okay, well, you only have 3 cars in your domain. So once you have used 3 of the colors, you're short. You can't have a 4th color. So it's really no accident that we have 3 cars in our domain and 3 colors in our codomain if we want to construct a function from A to B, which is both one-to-one and on-to. So here's the main theorem about bijective functions. Suppose that A and B are any 2 sets, and f is a function from A to B. Then f is bijective, in other words, it is both injective and surjective, if and only if we can find a function g from B to A, called the inverse function of f, such that for all A in the domain and B in the codomain, the composition f composed g evaluated at B is the same as B, and the composition g composed f evaluated at A is once again A. We call these the cancellation properties of f and g. Essentially, f and g cancel each other. So another way to say it is that f composed with g is I sub b, the identity function on B, and g of f is I sub a, the identity function on A. And just like when we define the identity transformations on our Euclidean spaces, the identity function on a set does essentially the same thing. If you input A into the identity function on A, you will also output A. So that is what we get if you input A into G composed F. So that's why we say that G composed F is the identity on A. Similarly for B, if you input B into the identity function for B, you will get the same element B. And if you input B into the composition F composed G, you will again output B. So F composed G is the same as the identity function I sub B. I just thought it would look nicer if we have A and B in alphabetical order, but that's just me. So we also write that G is F inverse, and that is pronounced F inverse, not 1 over F. Okay, in trigonometry, you might develop a bad habit of calling inverse cosine 1 over cosine. Wait a minute, 1 over cosine, that's secant of x, a completely different function. So for this reason, we also say that a bijective function is invertible, because the inverse function f inverse exists for a bijective function f and only for bijective functions. Remember, this is an if and only if theorem. F is bijective if and only if the inverse function g exists, and this inverse function g exists if and only if f is bijective, 1-to-1 and on-to. So I apologize that this is a rather long theorem. There is a short second part. Moreover, when f is bijective, this inverse function g is unique, and it has to be the function such that for all b in the codomain, g of b is a, where a is the unique element of a, such that f of a equals b. One more thing. Furthermore, g is also bijective. In other words, it is, again, both 1-to-1 and on-to. So therefore, by the first part, it has an inverse as well. Well, guess what? The inverse of g has to be f, the original function. So G inverse is F. So this is more naturally said as F and G are inverses of each other. So we see this in the cosine arc cosine example. Let's talk about the cancellation properties. If you have pi, for example, pi over 3, okay? So we did cosine of pi over 3 is 1/2, and this is the reason why arc cosine 1/2 is pi over 3. So compose that. If you input pi over 3 into cosine, you get 1/2, and then you input that into arc cosine, you get back pi over 3. That's the cancellation property for pi over 3. What if you input the 1/2? Well, that 1/2 needs to be input in the arc cosine function this time. So arc cosine 1/2 is pi over 3. Input pi over 3 in cosine, you're back to 1/2. Will this apply now to angles which are not between 0 and pi? No. Let's think about negative pi over 3. If you input negative pi over 3 into cosine, wait a minute, that's still 1/2. But the arc cosine of 1/2, we just said it's pi over 3. So if you input negative pi over 3, you output pi over 3. That's not cancellation. Negative pi over 3 is not the same as pi over 3. Luckily, you can't go wrong with the codomain, which was -1 to 1. You can't input any number bigger than 1 because there is no angle whose cosine is bigger than 1, or similarly, whose cosine is smaller than -1. So as you can imagine, it's a long theorem. The proof of that theorem is also long. I think it's about a couple of pages. So your assignment for section 3.6 is to outline that proof. It's not going to come from the homework. You're going to read that proof and you're going to write a short outline. Don't worry, I am making the skeleton of the outline for you. What I want to do with you instead, though, is I want to construct the inverse function for the function that we did in our example, which had nothing to do with numbers, but had to do with cars and about colors. We said that this function that we made is both 1-to-1 and 1-to. So according to that theorem that we just saw, there has to be an inverse function. G is F inverse. So how do we make the inverse function? Well, it is supposed to go from B back to A so that when you perform the composition, you're back where you started. Well, the idea is exactly the same as in pre-calculus. If H turns into R, who will R turn into? R has to turn back into H. So therefore, G of R has to be H. So really, I prefer the term reverse function rather than the inverse function. But of course, with centuries of tradition in mathematics, it's called the inverse and not the reverse function. So similarly, who will S go to? Well, where did S come from? S came from M. So therefore, G of S has to be M. Okay? And finally, we forgot about K. Where will W come from? So G of W has to go back to K. So actually, no, I was going down the list for the codomain. R goes back to H, S goes back to M, and W goes back to K. So we can quickly check, do we have the cancellation properties? Let's do the composition G composed F. So if you plug in W into, let's say K into G composed F, K goes into F first, so F of K is W, and then we input that into G, and G of W is K. Beautiful. So how about backwards? If we input W in the composition F composed G, then we input w first into G and we get K, and then f of K gives us back W. So therefore, f and G cancel out each other. Okay, so I hope you enjoyed that little detour into abstract mathematics. What we just did is a very important construction in mathematics, that whenever you have a function that goes from one set to another, and it is both injective and surjective, both one-to-one and onto, then you can construct the inverse function. And vice versa. If you can make this inverse function, then the function had to be both one-to-one and onto. So let's go back to linear transformations now. The title of the video said bijective operators. Okay, so can we have bijective linear transformations in general? Well, first let's define it. So a linear transformation, T from Rn to Rm, is bijective, the same word, if T is both one-to-one and onto. We will say equivalently that T is invertible, or T is a bijection, or T is an isomorphism. That's a really fancy word which appears a lot in mathematics. Okay, but remember the end of our last video where we talked about kernel and range and injectivity and surjectivity. What happens if you have a transformation from R4 to R5? So the dimension of the codomain is bigger than the dimension of the domain. So T cannot be onto. And now, what if you're going from R4 to R3? So this time you're going from bigger to smaller, and that transformation cannot be one-to-one. So in other words, if you want a transformation to be both one-to-one and onto, it has to go from one Euclidean space to the same Euclidean space. That's the only way that you have a fighting chance that it will be both one-to-one and onto. It may not be one-to-one nor onto, but if you have spaces which are not the same dimension, you are definitely not going to be one-to-one or onto, one or the other. So if you want your transformation to be bijective, then the two spaces must have exactly the same dimension. In other words, T has to be an operator. So that is why we have the title of this video saying bijective operators. So let us now rewrite our main theorem for bijective functions in terms of linear transformations, or as we just said, operators. A linear operator T1 from Rn to Rn is bijective. Okay? That is, the function T1 is injective and surjective. If and only if we can find another unique linear operator T2, also going from Rn to Rn, the inverse operator of T1, such that for all V in the domain Rn, T2 composed T1 of V gives you back V, and also T1 composed T2 of V gives you back V. In other words, the composition T2 composed T1 is the identity operator on Rn, and T1 composed T2 is also the identity operator on Rn. Now, when we did the general theorem, we had the identity on A and the identity on B. But because we have an operator, A and B are the same set. So we don't need to have two different symbols. They have to be the same symbol, the identity on Rn. So we also write, of course, that T2 is T1 inverse. Who is this T2? T2 must be the operator, so that for all W in Rn, treated as the codomain, T2 of W is V, where V is the unique vector from the domain Rn, such that T1 of V is W. Furthermore, if T1 is bijective with inverse T2, then T2 is also bijective, and T2 inverse has to be T1. So therefore, we will say that T1 and T2 are inverses of each other. Now, I do have a diagram down here which just about fits into our frame. Okay, so here's what's happening. T1 takes V to W, and then T2 takes W back to V. So therefore, the composition T2 composed T1 is the identity on the domain Rn, which takes V and gives you back V. So similarly, if you start with W and then input that into T2, you will get back V. So when you input V into T1, you will get back W. So the composition T1 composed T2 is the identity also on Rn, where this time W from the codomain is sent back to itself. So the only thing missing about that theorem is the proofs for linearity, additivity, and homogeneity. So I'm going to let you read those proofs in the book. They're very short, but basically you have to show that T2, when you input W1 plus W2, will give you T2 of W1 plus T2 of W2, additivity. And same thing if you input K times W1 into T2. Okay, so T1, T2, that doesn't sound very natural. In fact, we have been writing transformations as T without the subscript. So here is a more natural way to write what we just said. So it's the same theorem, just with different symbols. A linear operator T from Rn to Rn is bijective. So in other words, T is injective and surjective. If and only if we can find another unique operator, T inverse, also from Rn to Rn, the inverse operator for T, such that for all V in Rn, T inverse composed with T applied to V gives you back V, and T composed T inverse applied to V also give you back V. So in other words, T inverse composed T and T composed inverse are both the identity operator on Rn. So in particular, T inverse must be the operator so that for all W in Rn, T inverse of W is V, where V is the unique vector from Rn such that T of V is W. Moreover, if T is bijective with inverse T inverse, then T inverse also has to be bijective, and T inverse inverse is T. So this definitely looks more natural. Okay, we've seen that as far back as chapter 0 when we talked about real numbers. X inverse inverse is X. The negative of negative X gives you back X. So that was inverses for arithmetic operations. And now we have an operator on a Euclidean space Rn. We've come a long way. So again, we say that T and T inverse are inverses of each other. Okay, we're getting close to actual computations. We're now going to talk about invertible matrices. So, an n by n matrix A is said to be invertible if the linear operator T1, so we're going to go back to T1 and T2 for a little bit. The operator T1 from Rn to Rn corresponding to A, so A is the matrix of T1, is the bijective operator. So in other words, the operator defined by T1 of V is A times V. Okay, the matrix product A times V for all V in the domain is a bijective operator on Rn. In other words, it is both 1-to-1 and on-to. So, what are we going to do with this? Well, because T1 is bijective, there is an inverse operator T2, according to the last theorem. So that if you compose T1 and T2 in either direction, you will get the identity matrix, the identity transformation on Rn. Let's talk matrices. So what did we say? If you have the matrix of a composition, the matrix of T to compose T1, remember that turns into a matrix product. So we will have the matrix of T2 times the matrix of T1. There you go. But what is this equal to? This has to be equal to the matrix of the identity operator. All the way back to 3.1. So, of course, we also have on the other side the matrix of T1 composed T2. So we will get this. But this time, that will turn into a product of two matrices where T1 goes first, get up here, followed by T2. Okay, so what does this mean? If you have this invertible matrix A, that means that T1 is invertible. It has an inverse operator T2. It also has its own matrix. So now, if you compose the two operators, you get the identity. But wait a minute. Who is this matrix? What does the matrix of the identity operator look like? That's what we call I sub n. So, starting with T1, which is A, we produce a second matrix, T2. What's a good name for that matrix? Oh, of course, let's call it B. So here we have how to know whether you have an inverse matrix or not. Okay, so an n by n matrix A is invertible if and only if we can find another n by n matrix B such that A times B is the identity and it is also B times A. So reminder, matrix multiplication is not necessarily commutative. A times B and B times A could be completely different matrices. But for an inverse matrix, this inverse matrix B will result in a product with A to be the identity in both orders. A times B and B times A both have to give you the identity. Moreover, if A is invertible, then A inverse is unique. So in other words, if C is another n by n matrix, so that A times C and C times A are both identity, then C has to be A inverse, which is B. Moreover, the inverse matrix B is likewise invertible, and B inverse has to be A. So another way to say that is that A inverse inverse has to be A. So again, it's almost like we're back in chapter 0. X inverse inverse gives you back X. But this time, the A is a matrix. So, as usual, we can say that A and A inverse are inverses of each other. Okay, we made it. Finally, we're going to do some computations. So we're just going to focus on 2 by 2 matrices. In our next video, we will tackle 3 by 3, 4 by 4, bigger matrices. So for now, suppose that A is a 2 by 2 matrix, A, B, C, D. Then, A is invertible if and only if AD minus BC is not 0. In which case, we can compute the A inverse by this nice formula. Since AD minus BC is not 0, it has a reciprocal. And what do you put in the matrix for A inverse? A and D exchange position. So we have D up here and A down here. B and C stay where they are, but you have to put the negatives. Okay? So we're going to find out in a little bit why this formula works. All right, so let's take this example. So we have AD minus BC. We have 3 times 5, that's our AD, minus BC. So that's minus 9 times minus 2. as usual, be careful of those negatives. We will get 15 minus minus, minus minus is plus, so that's 15 minus 18, so that is negative 3. It is not 0, so therefore our matrix is invertible. Okay, so the formula says if you want A inverse, then you take the reciprocal of what we just computed, 1 over negative 3, and then you exchange the entries on the diagonal. So 5 goes up here and 3 goes down here. These two entries stay, but you change their signs. So negative 9 becomes positive 9, and negative 2 becomes positive 2. Okay? You can leave that answer as it is, or if you like, you can put that fraction inside. So you can change the entries. That first will be negative 5/3. We can write it this way. 9 over negative 3 becomes negative 3. 2 becomes negative 2/3. And 3 becomes negative 1. Okay, so why is this the correct answer for this inverse? Okay, well, let's verify. If you multiply A by its inverse, okay, so let's copy this down here, and then multiply by A inverse. So this matrix will go on the right, okay? So what do we get? 3 times negative 5/3, that's going to give you negative 5. And then we have plus 9 times 2, the negatives cancel, 18 over 3 is 6. So negative 5 plus 6, that does give you positive 1. Yay! What about the other entries? So let's clear this up. Same row, second column. 3 times negative 3, negative 9. Ooh, negative 9 times negative 9, positive 9. Negative 9 plus positive 9, 0. Next, we have negative 2 times negative 5/3, 10/3. 5 times, minus 10/3. So that's also 0. And finally, we have negative 2 times negative 3, 6 minus 5. That will give you again 1. Okay, so A times A inverse is indeed the identity. And of course, if you reverse it, we should also get the identity. Well, we have a computer to do this for us, right? So let's reverse. And of course, we also get 1, 0, 0, 2 by 2 identity. Why does this work in general? So let's take a look. We have our original matrix here. Let's do it on top. And then we have the inverse matrix over here. Okay, so we have times this. All right, so what do we get? AD minus BC. Oh, wait a minute. That's AD minus BC down there. So we get 1. This becomes 1. What about the next column over? Minus AB plus BA. So that's a 0. We have CD, D minus C minus CD. Again, that's 0. Last one. C times negative B minus BC. D times A, AD. AD minus BC, times 1 over AD minus BC. So we also get 1. So that's, of course, the reason why that reciprocal appears in the formula, so that it will cancel the AD minus BC in the first entry and the last entry. Okay, now what is wrong with AD minus BC being 0? Okay, just because this formula doesn't work doesn't mean that, well, could there be a different formula? Could there be another formula for the inverse? So let's think about that. That's related to an exercise in section 1.1, all the way back in section 1.1, when we talked about parallel vectors. So if you remember that one, two vectors u and v are parallel to each other if and only if something like u1v2 minus u2v1 is 0. Ooh. So if AD minus BC is 0, well, think of this as u1v2 minus u2v1. So the u's are A and B, and the v's are C and D. Ooh, so the first row is parallel to the second row. Okay, so wait a minute. If you get the RREF of that matrix, and the second row is parallel to the first, you can erase it. You can cancel it out by multiplying the first row by the multiple that you will get in order to get the second row, and then subtracting that. Ooh, type 3 row operation. So you will get a row of zeros in your RREF. Now wait a minute, what did we say in our last video? If you have a row of zeros in your RREF, then your operator cannot, your transformation in general will not be on 2. So you fail the onto property. And of course, as a bonus, sort of bad news actually, you also get a free variable. So therefore it is neither 1-to-1 nor 1-to-2. So that shouldn't be a surprise because we saw that happen also in our last video. So let's look at this second example. So we have 9 minus 15, negative 6, 10. So this time, what is AD minus BC? What do we get? So 9 times 10, 90, minus BC, negative 15 times negative 6. Wait a minute, that's also 90. So that matrix is not invertible. Okay, so there you go. We know how to tell if a matrix is invertible or it is not invertible. Okay, so for our final theorem, let's tie everything together. So recap. When is an operator bijective? It is both 1-to-1 and onto, if and only if it has an inverse operator. So we have this operator T inverse. How do we know when a matrix A is invertible? Well, the corresponding operator has to be bijective, both 1-to-1 and onto. But we said this means that there is a matrix inverse, B, so that A times B or B times A give you the identity matrix. So how could this be, no pun intended, how could this matrix B be related to the inverse operator? Well, of course, it has to be the matrix of the inverse operator. So, tying it all together, a linear operator T1 from Rn to Rn is bijective if and only if A, the matrix of T1, is an invertible n by n matrix. If this is the case, then T1 is also invertible, we said that, so the matrix of T1 inverse has to be A inverse. So another way to write it is that the matrix of T1, when inverted, gives you the matrix of T1 inverse. Okay, so that is our video for today. I hope you enjoyed it. I hope you enjoyed a little bit of abstract mathematics, because one of our goals in teaching you linear algebra is to invite you to learn more mathematics. So if you enjoyed what we just did, maybe think about taking a few more higher level math classes where we explore more general constructions for functions, for different mathematical objects, which are called groups, rings, fields, all sorts of things. And many of the properties that we see in linear algebra generalize nicely, and sometimes they don't, to these new constructions. So, as usual, this is Jude Socrates signing off. You will find me on Facebook, and you will find the 4th edition also on Facebook and at kendallhunt.com. So, until our next video, enjoy the rest of your day.